Right, so today we are going to learn a very important topic, that is perturbation theory. I actually uploaded this video yesterday, but it was very dark because it was already night, so I thought it's not that good to actually have a look at the video in that mode, so I just deleted that video and I'm recording it again. So this was most requested topic, and I request you to watch the video till end because I took lot of efforts to understand the derivation which I'll be explaining you today. The whole derivation, it took me 2 hours to understand, but finally I felt that it is very simple. I'll try to make it simple and explain you like I'll do my best to understand this particular video, okay? And then I'll be solving one question from your previous CSR which came on this perturbation theory, right? So what is the need of this theory? Firstly, see, Schrodinger wave equation is applicable for one electron and like one electron systems only. But as the complexity increases, as the number of electron increases, the Schrodinger equation, it becomes very difficult to solve that equation. Okay, in that cases, few approximation methods were used to solve the complex systems, and one of those methods is a perturbation method. That is, perturbation theory is used to solve those complex systems. Now, perturbation theory, it is of two kinds. One is your time independent perturbation theory, and second is time dependent perturbation theory. So this independent theory is also known as stationary perturbation theory or Rayleigh-Schrodinger perturbation theory, right? So today we'll be talking only about the explanation for time independent perturbation theory. So we'll be talking about this particular derivation regarding this theory. Okay, now how do you start is that, suppose you start with a physical system. Okay, this is your system, physical system, and the Hamiltonian of this particular system is H naught. Okay, Hamiltonian of some physical system is H naught, and this is your unperturbed Hamiltonian. What is the meaning of unperturbed Hamiltonian? There is no external force acting upon this particular system. Okay, it is free from the external forces, and psi n naught is your unperturbed eigenbasis wave function. Okay, now what I'll do is, from here the theory starts. The perturbation theory means that once you apply an external force on the system, what is the change? That is what we have to learn. Okay, now I'll apply an external Hamiltonian, that is an external force on this particular system. Okay, now once I apply my external Hamiltonian, what happens is that the total Hamiltonian H will be the sum of your initial Hamiltonian, that is unperturbed Hamiltonian, plus perturbed Hamiltonian. So H is equals to H naught plus H dash lambda. Okay, so lambda is the strength of the perturbation, that is the lambda value. If it is 0, it means H is equals to H naught, there is no perturbation. If lambda has some value, it means there is some external force acting upon the system. So lambda is the measure of the strength of the perturbation. Okay, remember this particular thing, like in my next pages I will be telling that from equation A. So you should remember that equation A is this initial physical system Hamiltonian equation. Okay, so the eigenstates of new Hamiltonian. Now after applying perturbation, whatever the A I have written changes to this particular equation, that is, there it was H naught psi n naught. Now as I have applied an external Hamiltonian, this is your resultant new equation. Okay, so psi n changes to your psi n naught plus ket delta psi n. So psi n is the total wave function, but this is the sum of the wave function, that is, this is before the application of Hamiltonian psi n naught, plus this is the because of the effect of the external force, this is the resultant added Hamiltonian. So the added wave function, sorry. So the total wave function is nothing but sum of your initial as well as the change in the wave function after application of Hamiltonian. Okay, so this delta psi n will be equals to summation of ck psi k naught. Okay, now what you have to remember is here that after application of the external force, your wave function will not be equal to your initial wave function psi n. Definitely there will be some change. So that change, it is represented as psi k, okay, but not psi n. That is the only difference you have to remember. Now also there will be change in the energy on the application of Hamiltonian. So what is the change in the energy? The initial energy was En naught plus delta En. So what is our aim? We have to find these changes. This is what we have to find. Okay. So this I have taken, the same thing I have written again here. Now I'll apply all the changes which have been appeared in the system after application of the external Hamiltonian. Okay, so H is nothing but your H naught plus lambda H1. This I have got from my previous page, that is H is equals to H naught plus H dash lambda. And psi n, what is the change in psi n? This is the change, I have written that here. Then energy change is this particular thing I have written here, and psi n is equals to this thing. Okay, so this is the total the new equation formed after the application of Hamiltonian. Now what you do is, don't look at this thing, just simply multiply your this term with each of them. H naught with this, H naught with this thing, lambda H dash with psi n naught, lambda H dash with delta psi n. In the similar fashion, just multiply these equations. Now once you multiply each thing, you will get this particular equation. Okay, now after this we have to simplify this. How do you simplify this? Is that from your A equation you will get that H naught psi n naught is En naught psi n naught, right? This is from your equation A. So directly I will substitute in the place of H naught psi n naught is equals to En naught psi n naught. Okay, from equation A you get this, right? And here lambda H dash and lambda H dash there in these two terms. So I will take lambda H dash common, and you will be left out with psi n naught and delta psi n. But you know that psi n naught plus delta psi n is equals to your psi n. So directly lambda H dash ket psi n will be your resultant here. So I have written these two terms and I have clubbed it in a single form. Okay, and then this is what is the left out, H naught plus delta psi n. Where did this go? En naught psi n naught. The same thing is present in your right hand side. See, you are equating these two, so this is equals to this. So these two are equal, so I will just cancel these two things. So you are left out with this equation, and that is equals to this term, and this term. So you are left out with these three terms. So I have written these three terms over here. I hope you are clear till here. Now what we will do is multiply by psi n naught on both sides. Now why do you do this? See, our aim is to calculate delta En. Okay, we have to find energy and wave function after application of the Hamiltonian. So we have to find out delta En. To know this, we have to eliminate this psi n naught. So what I will do is I will multiply with psi n naught on both sides. Multiply with psi n naught on both sides. So what you will get is this particular thing. Simply multiply. Don't look at my book, it will be complicated. If you multiply, psi n naught will come here, here as well as here. In all the terms, just add psi n naught. So you'll get this particular term. Now here you have to concentrate. This step is very important because here you use your basic quantums, the orthonormal, orthogonal conditions, whatever we have learned, like psi I, psi j is equals to 0 if I is not equals to j, and psi I is equals to 1 if psi j is equals to 1 if I is equals to j. This you have learned in your basic quantum, right? That you have to apply over here. Now delta psi n naught and psi n naught is equals to 1. Okay, this is the condition of orthonormal basis, so this becomes equals to 1. Now this is very important. See, delta psi n, what I have told you, delta psi n is psi k. Okay, something other than your initial Hamiltonian wave function. Okay, so this psi n will not contribute anything to your existing free Hamiltonian, I can say psi n naught. So there is no contribution of delta psi n for psi n naught. So this term becomes equals to 0. The same thing is here, psi n naught delta psi n. So this term also becomes equals to 0. So these two terms becomes equals to 0 and this becomes equals to 1. So you are left out with these two terms, and that is equals to delta En. This is what is there in my next page. Okay, this 2 is equals to delta En. So delta En is equals to these two terms. Now what I have written here is that the same thing again which I have done in my previous steps, that From equation A, psi n naught h naught is equals to E n naught psi n naught. Okay, your free Hamiltonian equation I am using again and again. To get a simplified form of delta En, we just do it. Okay, so you get E n naught psi n naught. Delta psi n is as such, you just substitute these two terms. If you write this thing here, this is the resultant, E n naught psi n naught delta psi n. And we know from the previous page that there is no contribution of delta psi n for psi n naught. So as there is no contribution, this becomes equals to 0. So the whole term becomes equals to 0, and your delta En will be equals to this particular thing. I'll just, as the lambda is constant, I'll just write it in before the brackets. So delta En is equals to lambda into this term. So this is your second equation. We'll still try to simplify this equation because this is very complicated. As psi n naught, we know it is unperturbed wave function, but h dash is a perturbing Hamiltonian and psi n is a full wave function. It is very difficult to determine the full wave function, so we will simplify this again. And psi n has an expansion, and its expansion form is psi, total wave function psi n can be written as psi n naught plus lambda psi n1 plus lambda square psi n2 plus so on. Okay, just simply take this particular equation and substitute in the place of psi n. So delta En is equals to lambda psi n naught h dash into psi n, the whole thing just substitute here. Okay, now delta En is equals to lambda into, multiply this whole term lambda psi n naught h dash with each term psi n naught psi n1 psi n2. Okay, multiply with each term, so you will get this particular equation. Now as everything is same over here except for the last term, psi n naught h dash is common everywhere, so I will just write the simplified form of this term as delta En is equals to summation s is equals to 1 to infinity lambda power s psi n naught h dash psi n s minus 1. Why I have written s minus 1? Because if you look at here, the power is 1, so here it is 0. If it is 2, it is 1. So this term s, now here the term will be always 1 less than the constant power. If lambda is here 1, this is 0. So lambda power 1, 1 minus 1, 0. You will get this term. Okay, so this is the simplified form. Now this whole term psi n naught h dash psi n minus 1, we just write it as ENS. Okay, for simplification, lambda power s ENS is considered as this term. So this is what we wanted, the energy term. This is your energy term ENS, and this is equals to your psi n naught h dash lambda n s minus 1. This is very important, as this is the actual energy equation which is used for your first order and second order corrections. Now for the first order correction, just in the place of s you write here you write 1. So En1 will be psi n naught h dash psi n naught, because 1 minus 1 will be 0. So this is the energy calculation from the perturbation theory. Now we will try to understand the wave function calculation. Okay, so this was the general term which we got after application of the Hamiltonian. Okay, I hope you remember this very first equation. Okay, from this now we will try to solve the wave function for the for this particular perturbation theory after application of the new Hamiltonian. Okay, I've written it again. So what was the change after application of Hamiltonian? H naught plus lambda h dash, and psi n is nothing but your the expanded form, what I have written in my previous page. The same form is written even for the energy, En naught plus lambda En1 plus so on, and again psi n, the same term I have written here. Now this is very simple. Directly you correlate the lambda powers and write down the first order second order corrections for the wave function equation. Okay, for the zeroth order you have to see where is the lambda 0 adjacent to wave function, because our aim is to calculate the wave functions. Okay, don't look at this lambda, we have to look at the lambdas of this particular wave function equation. So if you look at here it is lambda power 1, it means this is lambda power 0. So I directly write lambda power 0 is equals to h naught into psi n naught. Okay, this into this is equals to, where is lambda power 0 over here? If there is nothing, this is lambda power 0, E n naught into lambda n naught. Okay, as these two are equal, these two are also equal. So I want lambda power 0, so correlate these terms where the lambda power is 0. You get this. Now first order, how do you get your first order? Just correlate the lambda having the power 1. So where is lambda power 1? H naught into psi n1. Here the lambda is 1, so H naught psi n1 plus, here also the lambda is power 1 with when you multiply with this wave function. So I'll write H dash lambda psi n naught, okay, because you'll get lambda power 1 if you multiply this two as well as this two. Now similarly multiply over here, E n naught into lambda psi n1. Here is the lambda power 1, so I'll multiply this thing, and whereas I'll get lambda power 1 here. Okay, this is lambda power 1, so E n1 into psi n0, that is what I have written here, this fifth equation. No need of this, simply it came in like it was there in the book, but not required. So from this equation what you will do is, see, this is a first order perturbation. Now first order perturbation means there is some perturbation applied on your existing physical system having H0 Hamiltonian, right? Now as the external perturbation is applied, it means there is some other wave function acting upon it other than your psi n0. So that external wave function cannot be your psi n, it can be other than that. So we'll just consider it as psi k. Okay, psi cannot let it be the external Hamiltonian acting upon the system. So just simply multiply that psi k naught with in the equation 5. So everywhere just write psi k naught H naught psi n1 and multiply with this and this. I have written the I have directly written the next step. What I have to explain here is that psi k naught H naught psi n1 minus, I have taken this term to the left hand side, is equals to this particular thing, and I have taken this term to the right hand side. Okay, just simplify this equation in this form, you will get it. Now look at this equation. This equation here, the psi k naught and psi n naught. So I have told you that summation psi I psi j is equals to 0 if I is not equals to j. We know that k is not equals to n, so this term comes out to be 0. Okay, so this term is equals to 0. The other three I will just write down over here. Now what you do is, you just simplify it by multiplying with minus, because here it is minus. So just multiply with minus, you will get this term psi k naught H dash psi n naught is equals to, here you will take psi k naught psi n1 common in both. So just take common and write the energy values over here. So psi k naught psi n1, see, our aim is to find eigen equation, right? So for the eigen equation you need psi n1, this is what you have to find out. So simply write this over here, and then this is divided by this thing, energy. Okay, so this is your psi n1, this is what is required. Further we simplify it because we want only psi n1, not psi k naught. Okay, so how do you eliminate psi k naught? Just multiply by psi k naught on both sides, because we know that orthonormal bases will form 1. So to eliminate this, we'll again multiply with psi k naught on both sides. Now once we multiply, we'll get this term, and this becomes equals to 1, and we'll get a required first order correction to the wave function, that is this particular thing. Okay, so this is your final equation. This I have simply written as H dash kn, as in the matrix form we can just write the psi H dash kn psi k naught by energy E n naught minus E k naught. This is your first order correction term for the wave functions. So this is all perturbation theory. It is more mathematical, but once you understand this whole thing, it will be easy for you to mug up the final equation for your exam point of view. It is difficult to mug up the final equation without understanding the derivation. Okay, that is the only reason I have taken up the derivation, so that it will be helpful for you during exam. See, this is the question I want to explain you, but the formula is that this is the form energy, second order correction energy equation is this. Now I cannot tell you that use this equation, it will be very silly. Okay, I'll try to even solve this equation over here. Now we have to find second order correction. So we already know this energy thing. From where do we know this? This over here. right? E and S is psi n naught h dash psi n s minus 1. That is what I have written here. But we have to find out the second order correction. So E n 2 we have to find out. So what will be psi n s minus 1? Psi n1. Okay. Now you understood why did I solve the first order wave function over there? Because to find the energy of the second order correction, you have to know the first order correction wave function value. Okay. And that's how it goes. To find out the third, second is used, and so on. So your En2 will be psi n0 h dash and psi n1 value. This what we have got over here. This I'll just substitute over here. Psi p0. Here I have taken k. It can be k, p, m, whatever it is your wish, but other than n. So you can write k, not a problem. Don't think that p and k are different again. You can just write k, not a problem. Okay. So other than psi n, just write down the equation which you have got in your previous page and simplify it. So psi n naught h dash, psi n1 value you have written here. The next step will be summation p is not equals to n, psi n naught h dash psi p naught. Here psi n naught h dash psi p naught, and this whole term is here. I have written separately. So these two things are same, right? It is psi n naught h dash psi p naught, psi n naught h dash psi p naught. It means this is just square, psi n naught h dash psi p naught square. Can I consider like this? Yes. And in the denominator you have energy. This is the formula I have used here for the second order correction question appeared in your exam. Psi m naught h dash psi n naught square E n naught minus E m naught. Okay, now you understood how do you get this equation for the second order correction. Okay. So the question was the unperturbed energy levels of a system. They have given energies, and second order correction for the ground state in pressure of the perturbation V. They have given perturbation values. Okay, has been found out to be. So from the equations we can see that n is always your ground state perturbation. Okay, so ground state perturbation means zeroth level, and then first and second and third. So you have been given with the two perturbation values, three perturbation values. Okay, so this is the formula used, and n is a ground state, so n is equals to 0. Now for second order perturbation, this is the formula. Okay, and you are not taking the further thing like V12 is given, but 0, 1 and 2. So this is not at all required, only these two are required. So this is the change in the perturbation which we have got from our derivation. And what is the given change in the perturbation? The first one is V10 square plus V20 square and the energies. Okay, so just simply substitute the values. The V value, it is given as 2 and 4. So 2 square 0 minus 2 plus 4 square 0 minus 4. On solving you will directly get your answer, that is minus 6. Okay, so this is the way you have to solve. I really hope you understand this derivation, because I really tried my best to make it easy for you, but still if you have any doubts anywhere in this particular derivation, you can comment down and you can clear your doubts, as I'll be very happy if you can directly ask me doubts without any hesitation. Okay, don't think that this is such a small doubt, what will I think, or nothing like that. You can ask whatever doubt you have, just comment down. I'll be ready to answer any kind of questions you ask me. Okay, right, thank you then.